Next we have Dr. Elizabeth Fisher, who will be talking on the contribution of mouse genetics to our understanding of Down syndrome. Humans and mice share a common ancestor who lived about 80 million years ago. And so we have common genes and genomes that function similarly. So Elizabeth will tell us how really it benefits research into Down syndrome. Dr. Fisher.
Well, I'm going to start by thanking you so much for letting me come here and tell you something about our work. And the us in question is my colleague Victor Tabunovic. He and I are mouse geneticists and have worked together for about 20 odd years on producing mouse models of Down syndrome. But before I start, there's a couple of things to say. One is that I'm actually presenting two talks. I've got two sets of slides. The second set being from Bill Mobley, who many of you here know, who's a Down syndrome expert working in the States. So if I'm still talking after about 2 hours, somebody's going to wrestle me to the ground. The other thing is that because I sent the wrong piece of paper to the organisers, you've actually got my full CV in the programme, which is desperately interesting to me, but probably not to you. So I am a mouse geneticist, and you might think, well, what on earth have mice got to teach us about Down syndrome? So for the next 20 odd minutes, or 2 hours, I'm going to take you through the very fascinating world of mouse genetics. So why mice? Why do I spend my life working on these animals? Well, it's because of evolution. We've all evolved from the same ancestral organisms, and if you look at this little animal here, there's its head, there's its backbone, and there's its tail. That is a fossil of something that's about maybe 15 centimetres long. That's great-great-great-great-great-great-grandma for all of us, for us and mice. It's in the fossil record. You can look it up on Wikipedia if you want to. And that's one of our ancestors. But in fact, we and mice split off from an ancestral organism about 80 million years ago. But it makes us distant cousins. So that means that we share the same genes with mice. Those genes are doing the same things. We've got the same biochemistry, the same chemicals in our cells. We've got the same physiology. We have hearts pushing blood around, mice have hearts pushing blood around, etc. So that means that we get the same disorders. In other words, we can model human disorders in mouse. And why might we want to do that? Well, if we can justify it scientifically and we can justify it ethically, and those are important points, it means that we can actually manipulate the mouse genome. We've got the techniques, the tools, the genetic tools at our fingertips really these days to make any kind of human disorder in a mouse. And the big advantage of doing that is that we can then look at all tissues at all stages, from the very, very earliest development of the embryo, even at the single egg and sperm stage, all the way through to the aging animal. Mice age in the same way that we do. They turn grey, unbelievably, they put on weight. We all know it, those of us over 50. And we can also carry out therapeutic testing in those animals. So what I spend my life doing is making mouse models, manipulating the genomes, the genetic code in mice. And the reason that we all do that is because we can then use genetic tools to get at the genes, the individual instructions in someone's cells that affect biochemical pathways that can give rise to different disorders, whether it's Down syndrome or anything else. And this information is important because it will then allow us to target therapies for aspects of Down syndrome or indeed anything else that we're studying. So how does this relate to Down syndrome specifically? Well, many of you probably recognise this person. This is John Langdon Down himself. As you heard earlier on this morning, he was a Victorian English doctor. He was a poor boy, the son of a shopkeeper who ran away to London to become a doctor. And he was particularly interested in people with learning difficulties. So in 1862, he published a paper with a group of people who we would now say have Down syndrome. And that was really it for a long time for Down syndrome research, at least for genetics. And then another doctor, a French doctor this time, Jérôme Lejeune, discovered something astounding. In 1959, he he decided to look at the chromosomes of people with Down syndrome and found, of course, what we all know very well, that if we look at the chromosomes, people with Downs have 3 copies of chromosome number 21. And a chromosome, of course, as you know, is just it's a big, long molecule that carries lots of genes, lots of the instructions for what makes us who we are. So if we think about all the genes are on chromosome 21, and we know that people with Down syndrome have an extra copy of all those genes, and we're now left with this question, well, all right, if we know that, which genes are responsible for which features? And that's important for thinking about understanding Downs and targeting therapies. So this is my staggeringly accurate picture of chromosome 21. There we are. It's a long, thin molecule with a blob in the middle. And one of the difficulties that we face is if we want to model Down syndrome in humans, the chromosomes have got slightly jumbled up during the course of evolution. So human chromosome 21 actually corresponds to 3 different mouse chromosomes, mostly mouse chromosome 16, a little bit of mouse chromosome 17, and a bit of mouse chromosome 10. But what we can do is we can use a very fancy new technique that came in probably not that long ago, probably only about 7 or 8 years ago, and it's called chromosome engineering. And so I've turned into an engineer. What we do is we move these very, very big bits of DNA around, and we create new models in which those individual portions of mouse chromosomes are now present in 3 copies that are exactly mimicking what's going on in the human genome. Very few labs can do this, but nevertheless there is a worldwide effort, and the names that are very important here are Eugene Yu, working in the USA, Roger Reeves in the USA, Jan Hero working in the USA, and Victor Lee working in London. And for those of you who follow Down syndrome research, you'll keep coming across those names because these are the groups who are producing many of the new models. Victor and I did something slightly different a few years ago in that we decided we'd put human chromosome 21 into a mouse, and we thought we'd do this because that would then really exactly mimic what's going on in the human situation. It would give us the full set of correct genes, and those genes, the bits of DNA that just give instructions to cells, they would all be present and working at the correct levels. So we did that, and this is our normal mouse. Wild type is just a genetics term for normal. And this is our Down syndrome mouse. It's called a TC1 mouse. It's got a very long name, a transchromosomic, but essentially that's a Down syndrome mouse. Now looking at it, it's absolutely no different from its normal brother, is it? I can't tell the difference. I've been working with these mice for years and I can't tell any difference between one another. But if you look at the DNA of those animals, this mouse here has human chromosome 21 inside it. Now, has that actually been helpful to us? Well, it has. So if we could start the first video, this is one of the tests that we do of mice to look at their motor coordination. Oh, there we go. Watch that mouse. We're trying to look at how the mouse walks. If you could start it. There we go. So he's over a cushion, in fact. He's using his tail to balance, but he's not having any difficulty at all getting back to the end of the rod. So that's a normal mouse walking. In the second video, if you could start that, look at the mouse again. Look at how he's walking. Oh, we go back. Look at how he's walking. He's having a lot of difficulty. He's not using his tail to balance properly, and he's really not having a very good time. I do want to reassure you that if he fell off, it would be onto a soft surface. So we know that, in fact, although we can't tell the difference very easily by eye, there is something going on in the mice that have human chromosome 21. And this may tell us something about gait and about movement in Down syndrome. I'm going to pick out another couple of features, but there's many years of research on these mice. We've heard a lot already about heart defects. If we look in a normal mouse, I mean, frankly, I wouldn't recognise one end of a heart from another. This is other people's data, but I'm going to point it out to you anyway, shamelessly. You have a normal, what's called a septum, separating the chambers of the heart. In our TC model, you can just see arrowed that there's a hole. And it turns out that that exactly mimics what's found in human Down syndrome. Here's a really interesting thing. I know that there's a talk later on in this Congress about Down syndrome and cancer, because many of the people here, or several people here, have worked on cancer in Downs, and it turns out that for some types of tumours, for example breast cancer, there's a reduced susceptibility in Down syndrome, something about having that extra